So this is just to explain that, this particular slide just to explain that if early perceptrons can't solve very complicated problems. I'll just show you guys this one and kind of highlight it. This is a very example of a very simple problem. All of the answers can be fit on one side, and all the positive yes answers can be fit on one side, all the no answers can be comfortably fit on one side. But then in life, you know that there are sometimes when you make a graph, they don't fit nicely on a problem. Like maybe you're collecting some statistics on something and you graph it, it doesn't fit nicely on a line. So problems like that, if you ask a perceptron to guess, should I do this or should I do that, it can't really figure it out. So it's kind of complicated, so I won't go too deep into that, but at least you get the main idea of the limitation. So to solve that problem that we saw earlier, they realized that they could start stacking perceptrons on top of each other and become more fine-tuned, more or less. So this is when neural networks are. First it was just a perceptron, one single neuron, but now they started stacking it together, multiple neurons working together. So these are the inputs. This is a perceptron. This too is another perceptron. So this guy, let me start with these guys. These guys, they take direct input, and then they're very good at finding very fine specific details. And then they pass it on to this guy, and this guy, he can look at a more bigger picture. So long story short, these guys will find some very specific detail. He might be tasked with finding right edges, and then he might be tasked with finding left edges. And then this guy will put the right edge and the left edge together and figure out the combination of like the different edges. So they go from like fine details to more complicated details. And then it comes to the end of it, and then it makes a final conclusion. And he decides, okay, I see the edges are there, there's no corners. And then since there's no corners and there's like a circular element, the answer must be a circle, something like that, you know what I mean? So it becomes more complicated. So this is again, this is all about recognizing shape. They're still on recognizing shapes. First, the very first perceptron, it was like just deciding yes or no, present or not present. But when you want to start recognizing shapes, you need to recognize edges and stuff like that. So then you start with this. But then, what about a very complex shape that's not a perfect circle or something like that? Now you start to have problems, and that's because there's two main problems that I'll point out about these multi-layered-perceptrons. No spatial awareness. So spatial awareness is your ability to tell the difference between, like Chris is sitting closer to me than Nina. My ability to detect that one person is closer to me than the other, that's spatial awareness. So perceptrons couldn't tell spatial awareness. And the reason is, when a perceptron is reading things, so when a perceptron is reading this, he's not actually just collecting all of this information up there, looking at it. What he's actually doing, he's looking at this guy, then he looks at this guy, then he looks at this guy, back and forth like that, all of them one at a time. And then at the end, he makes his prediction up. But he has no way to tell that this second guy is underneath that guy, because he's just reading them all in a straight line. He has no ability to detect them all together. So that's why they couldn't detect spatial. They were just reading everything in a straight line. Even though you show them a square, in their mind, it was just a straight line. And then the other thing too is the parameters. So you imagine every single one of those squares that we were looking at earlier, you imagine every single one of those squares has weights on it, and it has biases on it. Now you imagine you have lots of pixels to look at. How many weights and biases you're going to get? The number is going to get very, very high. And those early computers, they can't process that much information. So you have two big problems that it put, the spatial awareness and also too many weights and biases. Okay, this last one is a bit more complicated. I won't really talk about it, but it's a bit more to do with calculus. It's a calculus problem. And then later on, they figure it out. So I won't go into it because that's like a bit complex. Okay, so now we come to convolutional neural networks. So all of the image recognizing ONMs today, they're basically more complicated versions of this one. So this is when they figured out how to really detect images. So remember, the first problem I mentioned was spatial awareness. Couldn't detect the relationship between pixels. Oh, sorry. First, let me just explain what this thing is that you're looking at. So this was, someone wrote a number 7, and then they took a picture of it, and then they put it on an image. Huh? And then they, every pixel of that image, they assigned a number to it. So this, all of the places where the 7 was written, you see it says 1, meaning the pixel was activated. All of the places the pixel wasn't affected by it, 0. That makes sense, right? Any questions about this, or does that make sense? It makes sense. Yeah. So this is just the image of a 7, and each of these numbers represents whether the pixel was on or not, or how on it was. Some of these pixels are like 0.5. You can't really see it, but it's like 0.5 because the pen ink must have like smidged a bit. So that's why it wouldn't be a full one. Okay, so that's the input, and then they read it, and then they put it onto a kernel. This is the second layer, a convoluted layer. Remember, multiple perceptrons connected to each other. So this input, put it to a convolution layer, and there's another layer here too as well, back and forth, and they feed the information back and forth to each other. Okay, so the big improvement that happened with CNLens that allowed to solve that spatial awareness problem and the weights problem is this guy here, kernel. So a kernel, it's like a field. It's like a little window, and rather than looking at each pixel individually, you see it's looking at multiple pixels at the same time. So now, thanks to the kernel, we can tell that this guy is underneath that guy, this guy is diagonal to that guy. We can tell a relationship. It's only for a very small region, but at least we can tell that there's a relationship there. And the other thing, these weights. So now you don't have to apply weights to each individual pixel. You put the weights and tie it to a specific kernel. And what happens is each kernel has a unique set of weights, and that helps it detect a particular pattern. So like, remember I said about left edge, right edge, top edge, some of these texture, speed. Weights make the kernels unique, and it helps it detect that. Okay, yeah, and then sorry, it does the math with that, and then it comes into the output, and it puts the output here. So this one refers to all 9 of these, and this one will, once the kernel slides over, this one here will refer to the next 3. It will sort of slide across in a line, and then it outputs there. Now, Chris, can you spot a difference in the size of this one and the size of this one? Well, what's the difference? Just look carefully. Are the sizes the same? The size of the information. This one's a bit bigger. Yeah. That's a problem, isn't it? We're trying to reduce our problems, but now we have a new problem that's kind of forming along the way. I'll come to how they solve that problem later, but this next slide here is just to highlight what I was talking about. So these are each unique kernels. This one detects top edges. So the top edge is light, white. And then what's the opposite of a top? A bottom, so it's dark. This one is the opposite. It detects bottom edges. So bottoms are light, tops are dark. And this is like for left, I think, and that's for right. So they do that individually. So each of this here is one of those kernels figuring out the information. So it figures out all of those information, and then you see this pooling. Remember the thing I just said about it stretching it there? You need another layer that cuts out the fat, cuts out the unnecessary information. That's the pooling layer. So it looks for patterns, cuts out the fat, and then it passes it here to be classified and find the pattern. So at the very end, after it finds all of these patterns, these fully connected layers will connect all of the information, and then it will pass it here, and then it gets the output. So that's like convolutional neural network. I zoomed in and I explained the kernel first to give you guys that, and then now I was like, this is the bird's eye view of how it works. So any questions on convolutional neural networks? Sorry, I'm going in depth a bit. Yeah. This will all lead into explaining the transformer layers, especially this diagram. I'll put it on again later and we will see how it leads to the transformer occurring. So even this convolution neural networks too, they had some problems. The hardware hadn't caught up yet. And also it could only have like a small number of layers. And one of these problems that existed earlier too is still going on. I won't explain that because it's too like math heavy to explain. But the big breakthrough finally comes in, well, two big breakthroughs, one after the other, in 2006 and 2007. So in 2006, this guy figured out a strategy for training modern neural networks. So what would normally happen is, remember, the AI will try to like train. If it gets the answer wrong, it will feed it back up and try to correct itself and go forward. But when you're feeding the answer back, if you have too many layers and you try to feed the answer back, it sort of gets stuck along the way because like that. It's too complicated for me to understand. But long story short, the deeper your layers, when they're trying to do the math to solve it, they use what in calculus we call chain rule. Remember the chain rule? We've done that in calculus. So when they're working on that chain rule, by the time it goes, it works backwards. They know the input and they know the output. And they're trying to adjust the weights. The weights are the thing that make it smarter. If the weights are not set properly, it will guess the incorrect answer. So they use their chain rule to try and work back to find out where the problem is. But if you have too many layers, the chain rule can't go that deep. Eventually though, this guy in 2006, he realized that what you can do is you can just freeze layers and adjust, use the chain rule on one layer. I won't go too deep into it because it's like really complicated, but that's kind of the breakthrough that this guy came with. Greedy layer. So you're greedy, you're just focusing on one, working on one layer at a time, and then you train them on. And then also in 2007, they invented GPU. So you saw that in the video that I played earlier. So this is a CPU and this is a GPU. The CPU, see, it has a big control unit, a cache. Cache is like its memory and arithmetic logic keyboard. So what happens is CPUs are really good at figuring out complex problems because they have a lot of memory and a lot of like math, so they can do complex problems. But these guys, they can't do complex problems because you see it's shrunk down, but they can do a lot of problems at the same time. So remember when we learned about this is all a very simple math equation. It's not a complex math equation. It's just taking this, doing that, getting there. It's not complex. You don't need a very complicated CPU to work it out. You can just get all of that and put that onto one of these small processors and just run it. So because of that, CPU allowed a big leap forward in computing neural networks and stuff. That makes sense, huh? Okay, so we went from using CPUs to solve these simple numbers to using GPUs to now looking at complex images. You can kind of see the relationship now. This one, it can't process a lot of things. This one can process a lot of things. And yeah, this is just reinforcing what I said. NVIDIA, now they can have 8 layers rather than just 2. Because I said, if it gets too deep, it can't work. But the guy figured out the better whatever, it solved that. And then also AlexNet. First, we were just dealing with 10 digits, handwriting. But when AlexNet came along, you can get 1,000 different categories and stuff. Okay, so now transformers. Now I'll introduce transformers. And I'll slowly start to connect the dots between the CLN, which is the pixels and stuff, and with natural language processing units.